All right, 102 students, here's your first exam. Let's go through it. This is a good time to kind of go through your thinking and see how your thinking maybe compares with my thinking. And I think there's going to be a lot to learn, even if you got a good score and, got most of them right. So I'll just run through this. This first one says, let's start off with an easy one. The subject matter of this course is physics, so hopefully that was an easy one for you. Let me remind you that the Canvas shuffles around the answers. So the answer is physics. It may not be B on your test, but wherever it got shuffled around to, again, the answer is physics. The height of a ceiling in this room is approximately 3 meters. Again, this is right out of chapter 1. Hopefully you see that we were just kind of starting and we had some homework problems like this just to kind of give you a feel for how big things are. You know, like this one's way too big, 30 meters, and this one, actually these two are the same, 30 centimeters, about the length of a paper. So, none of those would work. 3, here it says the diameter of a typical atom is, and of course, back to whatever chapter this is, 1, we're talking about 10 zeros there, and so that's what times 10 to the negative 10 means. And so 1, 2, 3, 1, 2, 3, 1, 2, 3, back to there. Number 4, the speed of 36 meters per second is equal to, that's the unit conversion. And so hopefully you did something like this. When you multiply by 1, you don't change anything, but it's got to be a creative one. So you want meters downstairs, so the meters would cancel, and kilometers upstairs, so that the meters would cancel with meters and you'd get just kilometers. And of course you have to make this equal to 1, so you have to say there are 1,000 meters in 1 kilometer. And so you're essentially multiplying by 1 because the numerator is the same as the denominator. That's a 1 right there. So we're really not changing anything, except it does convert it into the units of kilometers. Same thing here, we got seconds in the bottom, so we want to get rid of it. So I'm going to put seconds in the top, and then we also want hours in the bottom. And of course, then we have to make it a multiplication of 1. And so there are 3,600 seconds in 1 hour. So this one's going to need a little calculator work. It looks like I have to start off with a 36, and then I will divide by 1,000. Then I will multiply by 3,600. So that's pretty close to 130. So 4 should be B. 6, how many hours are required to make a 44-kilometer trip across the United States if you average 80 kilometers per hour? And so distance is velocity times time. And by the way, I skipped right over 5. Let me come back to 5 here. But anyways, the first 4, unit conversion and scientific notation and the idea of the units and what we're studying, that's all chapter 1. And so now we're getting into chapter 2 here. Sorry I skipped 5. I'll come back to that, but let me just finish this one up, because if I took then distance and divided it by velocity, I would get time. So we're looking at a distance of 44 kilometers, and we're going to be dividing it by 80 kilometers per hour. Fortunately, the units for distance are the same, and then the hour, when you flip and multiply, would end up on top. So we're going to have units of hours. Good. And so no real conversion from seconds or meters are necessary here. 4,400 divided by 80 looks like 55. So C would be 55. Going back to number 5 here, the average speed of an object. So again, this is chapter 2, and it's distance divided by time. So distance traveled divided by time taken. That sounds like the right one. Would be A on my paper here. Distance traveled multiplied, no. Change in velocity, no. Change it, okay. So definitely is A on mine, but it's going to get shuffled around. All right, going on to number 7, an object is accelerating. Remember, acceleration is a change in velocity. Velocity is both speed and direction. So if either one of these changes, and so it would be answer C here on mine, but it would be the one that says when its speed or its direction changes. All right. Here, a pitcher requires about 1/10 of a second to throw a baseball. The baseball leaves the hand at 40 meters per second. What is the average acceleration? So again, right out of chapter 2, it's the change in velocity. So the change is about 40 because final speed would be 40, initial would be about 0, so 40 meters per second would be there. And then the time is 1/10 of a second. So the number is 400, but that's not quite enough because you can see that there are 3 answers that have 400 in them. And then the units have to match. And of course, hopefully you already know that the units for acceleration are meters per second squared. But you can see that here. If you put your units, you would have meters per second, and then this downstairs, if I kind of write it as times 1/second, means across the top we multiply. And so we learned back in chapter 1 to treat our units the same way we would treat our numbers. And so 400 meters per second squared would be the right answer here. Now, I printed it out. Hopefully, I think Canvas doesn't do a real good job here. And they put the little caret there. So this would go meters second caret 2. And I probably should have said that back on number 3 on Canvas. When you have it on the screen, sadly, it writes it as a computer programmer would do and writes it as caret 10 to the minus 10. So some of your simple text doesn't have the superscript possibility. So that's why they do this little caret thing. All right. Number 9, if an object moves in a straight line with a constant speed. Well, straight line, constant speed, that's no change in direction, no change in speed, that's no acceleration. We can conclude that, I think there's more on the next page. Yeah, maybe, I don't know if I can get both of these on here, but the object has inertia, there is no forces acting on the object, there must be at least 2 forces object. This is really the best answer. It's answer D. There is no unbalanced force because we know that net force equals ma. And by the way, we started question 9, and so we've just finished the 4 questions from chapter 2. Now we're going on to the 4 questions from chapter 3. And chapter 3 had Newton's laws of motion in them. And so the best answer here is no unbalanced force, because we've got to put a 0 there to get a 0 there. And they're telling us in the words that the A would be 0. That's what this would mean right here, if an object moves in a straight line and at a constant speed. So there is no change in direction, there's no change in speed. So there's no acceleration. So 0 would be put here. So we have to have 0 net force. Now, it doesn't mean there's no forces, because you could have 2 forces that are equal and opposite, meaning the net force is 0. It also doesn't mean we can have at least 2. It does mean we can't have 1, because we can't, make a net force of 0 with 1 force. 2 would need there, but 0 forces would also work. So C is not a really good answer either. So that might be a little harder of a problem, because there are some options, if you will, that need to be given some thoughts. All right, well, let me keep going here. Number 10. 10 says, what is the magnitude of the net force acting on an object which is under the influence of a 3 Newton force to the south and to the east? So if I were to go 3 south and 4 east, I would have to combine those 2 together. And this is why we like to draw arrowheads, because it might seem like 3 and 4 make 7, but 3 and 4 only make 7 if they're in the same direction. So if you push with 3 and then 4 in the same direction, yeah, you get 7. But if you push with 3 to the right and 4 to the left, you only get 1, to the left even. And so the direction is important. That's why we, spent some time in this chapter talking about directions, and in this case, net force. And so for the last, I guess this is chapter 3, but for the last couple chapters, we've been talking about include the direction. And so you can see this better when you got a right angle triangle and you got Pythagorean's theorem, because 3 squared plus 4 squared would equal 5 squared. So this hypotenuse must be 5. And so the answer would be C in my case, but it would be 5 depending on where it gets shuffled on your test. 11, if a body is acted upon by a force of 10 newtons and it doesn't accelerate, I have a feeling we're going to come back to this here, we have to assume that nothing, the inertia is too large, that the net force acting on it is 0. Oh, I like that one. The law of inertia holds. So this would be it. Regardless of the fact if a body is acted upon by a force of 10 newtons and doesn't accelerate, the fact that it doesn't accelerate tells us the net force is 0. So that must mean there is at least another force, maybe more, in order to make the total forces come out to be 0. So the net force would be 0. If the Earth exerts a gravitational force of 20,000 newtons on a satellite in synchronous orbit, what force does the satellite put on the Earth? Well, this is Newton's third law, which says they are equal and opposite. So if the Earth puts a force on the satellite puts a force on the Earth. And they're equal and opposite. All right, so that's the chapter 3 and Newton's laws. Let's move into then what they called motion in space here, 2 dimensions, and we start off with a circle. So we got this race car moving in a counterclockwise circular path as shown in the diagram. Imagine that at this instant, the car is at point P, moving with a speed of 100 miles per hour. Now, in reference to this figure, in what direction is the net force pointing? It's pointing inward, and so the arrow here in D would be the best choice, and actually the only choice, because it is this centripetal one we talked about here, and I showed you in the video with a string spinning. Okay. By what factor does the centripetal acceleration change if the car goes around a corner twice as fast? Well, centripetal acceleration was v squared over r. So let's say you're going to particular speed, say v. Let's just say the sign says 30 miles an hour, so you're supposed to take it at 30 miles an hour. And somebody decides to double that speed. So mathematically, I would write it this way. So instead of hitting that corner at 30 miles an hour, they hit it at 60 miles an hour. And what may not be obvious to the non-science student is that when you double that speed with the exponent here, that becomes 2 squared v squared over r. Now, the v squared over r was the original acceleration that you would have had. It says by what factor did it change by. So it's 4 times. And the real key is to see that quadratic nature in here. And so make sure you kind of catch that idea in the math that it's v squared. And so doubling the speed makes it acceleration increase by 4 times. All right, a red ball is thrown straight down from the edge of a cliff with a speed of 30 meters per second. 30 meters per second. And at the same time, a green ball is thrown straight up with the same speed. So I've got one going up, that's the green one, and I've got one going down, that's the red one. And they're each going 30 meters per second. How many seconds later than the red ball will the green ball land. So the land's down here somewhere. And it's tempting to get lost in the details about how far is the ground. But it's really not necessary because it's the green ball that will go up to some maximum height, turn around, and be going down. Now, obviously, that will be later than the red ball. But here's the key to the problem. We know that it would be slowing down from 30 to 0 and then speeding up from 0 and then back to 30 because the speeding up has the same value of roughly 10 or 9.8 meters per second. So it's going to be going 30, so it's going to be just like the red ball. And so from here on, it does exactly the same thing that the red ball did. So really the delay is all because of what happens with the green ball as it goes up and comes down. That's the key. So we don't really need to know how far down that is. We just know that the green ball is going to repeat everything that the red ball did just a little bit later, depending on that delay. How long does it take for it to go up and come back down? So this is actually, I think, a pretty tough problem, just to recognize that. Now, of course, the other half of this is now we need to recognize how much time that would be. And since gravity slows it down by roughly 10 meters per second each second, if it's going up and it starts at 30, a second later it's going to be going 20. A second after that, it's going to be going 10. And a second after that, it comes to a stop. Then it begins to fall. So a second after that, it's going 10 down. A second after that, it's going 20 down. And a second after that, it's going 30 down. And it gets back to the same spot. So this up and down is 6 seconds. So the green ball has essentially a delay of 6 seconds. And then it does exactly what the red ball does. Which means then the best answer would be 6 seconds, which on my test is B. And again, on your test, it may not be listed as B. All right, well, again, let's keep going. Lots to show you here. And we haven't even got to the free responses yet. Which of the following statements about projectile motion is true? The horizontal and vertical components are independent. That is what I tried to emphasize. But watch this. The force on the projectile is constant. Yeah, like the force of gravity. It's always pulling down, always by the weight of the object. Oh, so I guess that one's true too. The acceleration of the projectile is constant through the air. Well, I guess the force is constant. Force, if that's the only force, then the acceleration would be that force divided by the mass. So anyways, those kind of go together. So the best answer here is D. It's actually all of these. And yeah, but they're all true. I was going to say maybe A is more importantly than the other ones, but they're all important. You should know all of them. And so the best answer is D. Which of the following statements about the moon is correct? Oh, okay, so now it looks like we're into chapter 5 here. Which is the gravitational one. But it says here, the moon has a constant velocity. Well, no. If I were to draw, say, the Earth with the moon going around it, the moon keeps changing direction. It may keep a constant speed, although that changes a little too. It's not a perfectly round orbit, but it roughly is. But it's certainly not in the same direction. And so this is really kind of back to the last chapter about motion in space. And so this does have an acceleration, does have a force. Anyway, so it doesn't have a constant. So no, it's definitely not that one. There is no net force. No, there must be a net force because it is accelerating. It is changing. The Earth exerts a stronger force on the moon than the moon on the Earth. No, that's impossible. Right? Newton's third law said they have to be equal and opposite. So it must be this one. The moon experiences a centripetal acceleration towards the Earth. Yeah. And so there's our motion of our moon. And even though this is a chapter on gravity, that's physics of this is really the motion in space. And so this is really kind of more about chapter 4 than maybe it is chapter 5. Al, the astronaut, weighs 800 newtons when he is standing on the surface of the Earth. What is the force of gravity acting up on him when he is in the space station orbiting Earth at a distance of 3 Earth's radii? Okay, so without maybe making this too extra hard and looking up some numbers, I might do something like this. So I'll just put capital R with a sub E for radius of the Earth. This would be the universal gravitational equation, and they're saying that Al, the astronaut, weighs 800. So if I were to put in the mass of the Earth, the mass of Al, the radius of the Earth, which I guess indirectly I can either look those up or know them. This kind of gives away the mass of Al, and we can look up the mass of the Earth, and we can look up the radius of the Earth. And if we put all those numbers in, we would get 800. All right. So hopefully you didn't take the time to put all those numbers in to get 800. They told you it's 800. But this is kind of the key. When he is in the space station orbiting at a distance of 3 Earth radii, and notice it says above the surface. All right. So now how far is Al from the center of the Earth? And I'm going to say Al is now 4 radii from the Earth. Because we have the radius of the Earth, then we have above the Earth 3 radii. So the total distance between Al and the center of the Earth is 4 radii. Just like when he was on the surface of the Earth, it was just 1 radii because there was no altitude. There was nothing above it. So it was the radius of the Earth plus 0. This is the radius of the Earth plus 3 radius of the Earth. And then this has that quadratic nature involved. And so this 2 would work on the 4, making it a 16 as well as the radius squared. And then here's why we don't really need to take the time to figure out what the radius of the Earth is or the mass of the Earth or the mass of Al, because we know all of those were 800 from an earlier statement. So this would be 800 divided by 16, which makes 50. So the answer is 50, or D in my case. And like I said, it'll shuffle around, but there'll be a 50 somewhere in there. Here's a little bit about gravity and tides. The highest high tides and the lowest low tides occur when the moon is. Okay, so we have the Earth, and a little bulge is created, both forward and back, depending on which planet we have. And this bulge, this elongated bulge, is the high tides, and where it sucked the water away from are the low tides. And so when the sun and the moon are in line with the Earth, and the moon could even be on the other side since it's a symmetric, both sides stretching of it. It doesn't matter which side the moon is on, but you're going to get your most stretching when they're in a line. If the moon was over here, what we call first quarter and third quarter, then the moon's trying to make a bulge this way, vertically I'll say, and the sun's trying to make one horizontally, and they compete with each other and, you know, make some kind of bulge at some kind of angle that is fighting with each other. So it's not as big as a bulge, and so your high tides aren't as big. Because they're not as big, they didn't pull water away, so the low tides aren't as low. So we're looking for the highest high tide, so they would be in line. And so when the moon is in between the sun and the Earth, you can't see anything. That's called a new moon. And when the moon is on the other side, you can see the whole reflecting face, so that's called a full moon. And so the best answer here is A, which is why if you spend some time at the beach, you'll notice you get your high tides and low tides in a given day, and then about a week later, they're not so big anymore, and then a week later they're big again, and then not so big, and then big again, as we go from a new moon to first quarter to full moon to third quarter, and finally back to another new moon. All right, well, I think we've got one more here on the universal law of gravity. If the Earth's mass were suddenly and magically reduced to half of its value, the magnitude of the Earth's acceleration about the sun would be. Now, this is important because the force depends on the mass of the two objects. So when you first look at this one, you might go, oh, well, that's going to change the force. And you're right, it does change the force. But the question asked for the acceleration. So the acceleration is the force divided by the mass. So in the numerator, did the force go down? Yeah, it went down by a factor of 1/2. But the denominator also went down by a factor of 1/2. And so if I had something like 8 over 2, and I take half of it now, I get 4 over and half of this, 1. See, that ratio is the same as that one. So if you reduce the top and bottom by the same factor, you don't change anything. And so that's why the correct answer for 20 is C. It's true the force went down by a factor of 1/2. It's true that the mass went down by a factor of 1/2. But the question asks for the acceleration, and both the numerator and the denominator went down by the same amount. So the acceleration doesn't change. All right. Oh, good. I was hoping to maybe finish this multiple choice within a half hour. So let's see if we can get close to that. All right, so here we get into our sixth and final chapter for this exam. It's about momentum, which has a greater momentum. And so I'll just remind you, momentum is a product of two other things, mass and velocity. They're very useful when they're hooked together. But here it says, which has a greater momentum, a truck at rest. So they say truck because I think they want you to focus your attention on a large mass. But you put a 0 there, means you got 0 momentum. Or a moving roller skate. Well, roller skate doesn't have much mass, but it is moving, so it would be something number bigger than 0. So I guess we're going to have to go with the roller skate. And the intent of this problem is just to make sure you're not thinking as momentum is mass. You know, the momentum is not mass. Momentum is both a product of mass and velocity. So it's those two quantities together. A stunt person is shot by a bandit, falls from a balcony into an airbag rather than into the ground. Will not get hurt because and so this was our contact time. We started this chapter by setting force is mass times acceleration, but you could rewrite acceleration as change in velocity over time. And so if you wanted to stop something, you know, like somebody falling from up above, their mass, you really can't really change or adjust that. Their change in velocity, you can't really adjust that because given the height that they're falling, they would gain a certain speed, and then you want to bring them to a stop. You don't want them to, keep going. So the key to keep the force small is to make the stopping time big. And so this is why we have airbags and seat belts that stretch so that if somebody gets in an accident, they're being slowed down as the seatbelt stretches. It's not just trying to hold them in tight and keep them from hitting their head on the dashboard, although that's a big piece of it too. But it is to make sure that the force is on structurally strong parts of their body, so that seatbelt, goes across their hips, and then the lap belt goes across their chest, and so those are strong parts of the body that can take big forces. But in addition to that, you want that contact time, so you want the seatbelt to stretch a little bit, or perhaps you have that airbag, so you let there be a cushion there, and it's not that it's soft, although anything that's soft then has a long contact time. So I guess those kind of go together there. But it's this contact time that we're really, really after. So when A says the momentum change is less for the airbag, the answer would be no. It's still the same mass and change in velocity. The momentum is less for the airbag. The impulse is less for the airbag. All impulse is just the change in momentum, so it's saying the same thing. So it's really D. Increase the stopping times means a smaller stopping force. So that's it. Small stopping times, huge forces. Big stopping times, small forces. That's how the math reads here. All right, assuming that your author jumps off the roof of a garage and lands on the ground, how will the impulse the ground exerts on him if he lands on the grass compared to if he lands on the concrete? So this is a lot like the last problem we did. I'll start with F equals ma, but change it to mass equals to change in velocity over time. This right here, this is the change in momentum. That is the impulse. And so like the one I was just saying, there really is no difference between somebody stopping by landing on grass or by concrete when it comes to the impulse. The person jumping down still has the same mass. They fall from a given height, so they gain a certain speed. So when they make contact with the ground, they have the same initial speed, whether they're making contact with grass or with concrete. And so they're changing velocity. And so this is the impulse. And so the impulse is going to be the same regardless of what we land on. So the impulse will be the same independent of the surface. But like the one before, we can adjust the force on the person by adjusting the time. And so jumping on something a little more squishable like grass, and it sinks into the dirt, you'll have a longer contact and coming to a stop, hopefully also bending your knees. I mean, oh man, the force, if you didn't bend your knees, would be enormous. Could you imagine just jumping off of even just a step and not either bending your knee or using your foot extended so that it hits it and can flex the calf muscle? I mean, if this contact is really small and so you just got like stiff knees and stiff ankles and go boom, oh, the force would be enormous. I mean, you might even actually break a bone. You certainly would probably strain a muscle in there or some ligament as you land. So you need to extend out that contact time. And of course, bending your knees and extending your foot is one way, but also landing on a material that gives and squishes is another big reason here. So all of that is to say the best answer for 23 would be that the impulse would be independent of the surface. The impulse is not the force. The impulse is the change in momentum, and that's the same. So be careful with the words there. That one, I think, can get a little hard just because if you might misinterpret impulse with force. You're like, oh, the force is less if I land on grass. Of course. So it's why, actually, you'll see, coming back to this, extending this contact time, you'll see like paratroopers, particularly if they're heavily loaded with material, so they got a lot of mass, they want to increase this contact time. So they'll come in and they'll have their feet hit, then they'll bend their knees, and if they do that well, they usually bend their knees in a way, and they come down and they're kind of in a rolling position. So then they hit the side of their shin, their knee, then they go into their hip, and then they go into their shoulder. And so all of that makes a stopping time really large, and therefore a low force. All right, well, I guess I was kind of talking too much, and I went way over my 30-minute goal here. One last one, and let's get on to the free response here. It says, 2 air track gliders are held together with a string, and so maybe we have a track, and we have cart 1 and cart 2, and it says here they're held together with a string. The mass of glider A is twice that of B. So I'm going to put a 2m here, I'm going to put cart B, and I'm going to put an m there. A spring is compressed, and so I'll put a little spring compressed between the two gliders. If the gliders are initially at rest, okay, so hopefully in your mind you're thinking about momentum. We got two objects, we got them interacting. In this case, they're pushing off each other instead of colliding into each other, so that might be a little tricky. But we know with the conservation of momentum, we know that the momentum before and the momentum after are the same. And so before it's 0. Which, of course, means that this one is going to go left and this one is going to go right, and they're going to have the same momentum. Now, not the same speed. You can see that because they have different masses. And as a result of the fact that they have different masses, they end up having a different speed so that they can have the same momentum. So if the gliders are initially at rest, so there it is, 0 momentum, and the spring is then released by burning the spring, so we cut it, burn it, whatever, what is the total momentum of both the gliders? Well, it's got to be 0. This would have a negative of whatever this one has positive, conservation of momentum. So no real calculations. We'll save those for the free response. But the correct answer there would be 0. All right, well, I hope you did well on that. Let me continue on with the free response. Remember the free response, there are 2 questions from each of the chapters that have some math in them, and that would be starting with chapter 2. So these first 2 are from chapter 2, and the next 2 are from chapter 4, or 3, excuse me, and then so forth. But this is the one about speed and velocities and accelerations and distances. So here, a race car starts from rest, has an acceleration of this much. How far does the car travel after 3.5 seconds? And so we have different ways of doing this. The 2 ways we could say distance is equal to average speed multiplied by time. Or we had a special equation that worked only if you started from rest. So this might be the appropriate one for number 25 because it works only if you start from rest, and this one does. Now, this one would work too all the time, whether you started from rest or not. So you can do this either way, but I think this is the one that comes to mind first. So I'll do this calculation. So it's 1/2, acceleration is 5.45, and I'll put meters per second squared. The time is 3.5 seconds, and you square it. So as far as the units go, remember that the square would square not only the number but the unit, so that's a second squared canceling off, and you'll be left with meters. Putting in the numbers, I have 1/2 times 5.45 times 3.5 squared, and we are looking at about 33.4 meters. Okay. Now, remember, this will be graded on a scale of 1 to 3. So if you did it all right, you get a 3. And like I said, there's a couple ways you could get to that answer. These 2 come to mind. Making a little chart comes to mind. And so if you do it all right, you get a 3. And if you do it pretty good, what some people do is they forget to square this, or they forget the 1/2. Okay, so things like that. That would be a 2. Things that are more off would be a 1. Not doing anything at all would be a 0. Okay, you can kind of self-grade yourself, but hopefully that one went pretty well for you. Here's another moving object. A moving object, in this case, passed into upper story window with a downward speed of 15 meters. So this already has an initial speed. So let's make sure we do not use this formula. That would be a mistake. 2 seconds later, how fast is the falling object traveling? Okay, so that's really kind of to help you with the bigger question, and then how far did it travel? So we know that it changes by roughly 10 every second. So if we start with 15, a second later, it's going to be going 25, and a second after that, it's going 35 meters per second. So that's what the acceleration of g meant, roughly 10 meters per second squared, which can be written as 10 meters per second each second, means increase your speed by 10 meters per second every second. So that's probably the easiest way to do it. You could put it in math and just go change in speed over time is acceleration. If you then put in your acceleration of 10 and your time of 2 seconds, of course, this would be 10 meters per second squared. Seconds, bring this over, and you could say your change in speed would be 20 meters per second. So if you add that to the 15, you're looking at 35. So the change is 20. Don't confuse that with the question. The question is, how fast is it going? 35. Now, really, I'll say that first question was really to help you with the main question, which is distance. And so distance equals to the average speed multiplied by time. And that's where I said, well, let's use the one that's always true, not the one that's just sometimes true. And in this case, we can't use the one that is sometimes true. So we got to use the one that is always true. So to get the average speed, we'll say, well, we start at 15 meters per second, and we eventually build up to 35. So you average those two. And that's how you average two numbers. You take the first and the second, and you add them together, divide by 2. And then you multiply it by your 2 seconds. So this 15 and 35 make 50, divided by 2. That in there is 25, and the units would be meters per second. 25 times 2 is 50, and the seconds would cancel off, and so you've got 50 meters. So I didn't give myself too much room to work in there, but that's the main answer to this question is how far did it go? 50. And of course, to figure that out, you got to get that speed after the 2 seconds. Okay. So there are the two from Chapter 2. Let's go to Chapter 3 here. Chapter 3, which has Newton's 3 laws of motion, says this: a 10.5 kilogram relief package has an acceleration of 2.25 as it's dropped from a helicopter to stranded victims in the canyon below. Now, clearly, there must be some air resistance, because it says what is the force of the air resistance. But we know that if there was no air resistance, the package would fall with an acceleration of roughly 10, 9.8. And so we've got quite a bit of air friction, which is purposely designed. And so this relief package probably has like streamers or a parachute on it so that it, slows it down. It's not going so fast when it hits the ground. It doesn't damage the supplies that are being dropped to the stranded victims in the canyon. So maybe they've been there for a few days and they finally discovered them, who knows, and they need some first aid or maybe some food and water before some humans can actually make it down into the canyon. So it still might be 6 to 8 hours before a human can get to you. And we've got to get you some medicine right away or something. Anyways, there's a relief package. So we're going to drop it in by helicopter. And this is the acceleration. And so step 1 of this is to remember Newton's second law says that the net force equals mass times acceleration. So the mass would be 10.5 kilograms, and the acceleration was given as 2.25 meters per second squared. And if I grab a calculator, 10.5 times 2.25 gives me a net force of 23.6. And remember that a kilogram meter per second squared is a Newton. So that would be the net force, and that's only halfway through the problem. I hope you don't stop there, because the problem didn't ask for net force. The problem asked for the air resistance. So maybe drawing a picture of this relief package. And so maybe the relief package is in a box. And so it's being pulled down by its weight, mg, but it's being opposed by the air friction. Let's call it little f. So the net force then would be its weight, mg, pulling it down, minus this frictional force. You see, this is what I mean by we haven't done the whole problem at this point. We've just got this number, this 23.6 newtons. And had they asked for net force, this much would have been the end of the problem. But now we have to put in our 10.5 times, and you can either put a 10 or a 9.8. Doesn't really matter there. But this is the second half of the problem, so don't stop halfway. So if I go 10.5 and multiply by 9.8, its weight is 102. And I have a feeling, since we did 10 so much, why don't I do a 10 times 10? Because I bet many of you are going to put a 10 here. And then if we bring this over and subtract 23.6, we will get a frictional force of 81.4 newtons. Or maybe a hair less if you do 9.8 instead of 10. So either is fine. Please know that it doesn't matter whether you do 9.8 or 10. But what's important is that you do both steps, that you do go ahead and connect the second step of net force with Newton's second law. And that can easily be overlooked. All right, well, another one here from Newton's laws of motion. And this is a lot like this one. It says, when a force of X newtons is applied to a 100 kilogram box with a frictional force of Y newtons. So I'm maybe pushing it this way with X, which means it's being opposed by Y. And it says the box has an acceleration of 2. So again, remembering that net force is equal to mass times acceleration, this would say X minus Y. Or you could even put plus Y if you wanted to let Y come out to be a negative number. And I suspect many of you will do that. So whatever Y is, we can have either plus or minus of Y. But I'm going to write it as X minus Y. And that would be 100 kilograms of mass times the acceleration they told me, which is 2 meters per second, which comes out to be 200 newtons. So X minus Y is 200. Now, that by itself, we can't solve for X and Y separately. We just know that the net force, so X minus Y, is 200. But here it says, when the applied force is doubled. So if I were to redraw this, now I would be pushing with a force of 2X. And an important part of this chapter was to realize the friction stays the same. So we still have Y. And we would have then a net force of 2X minus Y. And that would equal our mass times the acceleration, which in this case, the mass is still 100. And they say we get an acceleration now of 5. So that's 500. So we have an equation that says 2X minus Y is 500. So I would call that the physics of what's going on, noticing that the friction stays the same. The net force is combining the two forces together and using Newton's second law. So there's all the physics of it. We still got a set of math to do because we've got two equations, two unknowns. And so you've probably have learned to do things like substitution, elimination, Kramer's rule. This one actually looks really good for elimination. So I'm going to take the two equations and subtract the bottom one from the top one. So I've got 2x minus x. Well, that just leaves me with x. And I got a negative y minus a negative y. So that was really negative y plus y. So that's 0. And then I've got 500 minus 200. So that's 300. So there's the first step of mathematics. I got x equaling 300. Now, if I put that into, say, this equation over here, I got 300 minus y equals 200, which when I bring y to the other side, I would have 300 minus 200, which leaves me with 100, which you could write as a minus 100 if you had done x plus y. Okay, so y should be either a 100 or a negative 100, and x should be 300. So again, net force, don't just do net force and stop. You can't just say it's 200 and 500. The net force is combining the forces together. All right, so that was a pretty long one. That was a pretty good one. So that one's understandable if you struggled with that one. The other ones I think were straightforward. This has two parts, so that one may give you a little bit of a challenge. But this one maybe is probably the hardest one so far. I think there might be a harder one here. Let's go on to the next chapter. This is motion in space. In fact, this is the projectile motion. And so this goes back to a multiple choice question that we had, which I believe the answer in the multiple choice was about projectile motion, and the answer was all of the above. But the big one was that the x and y act independent, and that's what I'm going to do here. It says the arrow shot into the air, and so it says it has a horizontal speed of 25 and an upward of 35. Oh, I should have drawn that one a little taller up. But other than my drawing isn't angled as much as it probably should be because it's 35. It's more up than over. Hopefully you'll see that after 2 seconds, the horizontal speed, so I'll put v horizontal, would still be the 25 meters per second. That's the first half of the problem, going, well, yeah, the horizontal and vertical act separately, and gravity affects vertical, not horizontal. So whatever it starts with, 25, it keeps. So a second later, 2 seconds, 3 seconds, 4 seconds, 5 seconds, at least with no air resistance, there is no slowing down in the x direction. So it's still 25. Now, the vertical direction does change by g, which is roughly 10 meters per second each second. So if we start off at 35, a second later, we're going to slow down to 25, and a second later, we're going to slow down to 15. And that's probably the easiest way. Just kind of count it down. Again, you can do something like this. Change in velocity over time is acceleration, and you can put change in velocity, and you can put your acceleration as a slowing down, negative 10 meters per second, and you can put your time as 2 seconds, coming up with a change in velocity of negative 20 meters per second. So we're going to lose 20. So that's our change. So again, going back to our starting of 35, taking away 20 will leave us with 15. But again, the basic principle out of this chapter was that the horizontal and verticals act separately. So we do 2 calculations. The horizontal has no acceleration, so there's no change in speed. You can see that in the math too. Put a 0 there, no change in speed, so it keeps 25. And then the vertical does have a change of 20, so it would slow down by 20. Now, the 30 is kind of a continuation of that. It says use this information and say how far did it go. Well, distance, again, is average speed times time. And let me just do it twice. And so this is a lot like question 26, where we did a distance and time. The big difference, though, here is that we do it twice. And that was a big emphasis about projectile motion. Projectile motion is really like, and I kept saying this in chapter 4 here, that to do projectile motion, you really got to go back to our one-dimensional motion in chapter 2 and just do it twice. And so that's what this illustrates. I am going to do it twice. So my average horizontal speed is 25. Now, you could just probably write 25, but if you wanted to write it out, you could say, okay, it starts at 25, it ends at 25. You take those two numbers, add them together, divide by 2 to get its average for 2 seconds. And I should put meters per second. So 25 plus 25 is 50, divided by 2 is 25. So this is 25 meters per second for the average speed. For 2 seconds is going to be 50 meters. So horizontally, this thing's going to go 50 meters. Now, vertically, same idea. Vertically, you're going to start with 35 meters per second. And 2 seconds later, we have discovered that it slows down to 15. So there would be my mathematics to figuring out how far is it vertically. So the 35 and the 15 make 50. 50 divided by 2 is 25. 25 times 2 is 50. Seconds cancel off, and you're 50 meters also. So we're 50 meters high, we're 50 meters over. So the final and last step would be to say, all right, if you've moved over 50 horizontally and 50 vertically, then this is the diagonal of a square, if you will, which we know is the square root of 2 times 50. Or if you forgot that from your geometry, how about just Pythagorean's theorem? So if I call this C, C squared is equal to 50 squared plus 50 squared. And so 50 squared plus 50 squared is C. And taking the square root of that, we're looking at about 70.7 meters. Yay! Okay, so that one is, I don't know if it's, I was about to say it's hard, but I don't think it's hard as some of the other ones we saw, like 28, but it does require you to make sure you know the principle of the projectile motion. You got to treat the horizontal and vertically separately, like we talked about in the multiple choice. So, and then you do that. And then, of course, you've got a little geometry to do, in this case, Pythagorean's theorem, in order to figure out, well, where it is. Here is an object going in a circle, a small radio-controlled car with a mass of, and let's be careful with that one, it's in grams, is turning on a level ground with a speed of, and so they give us the speed in meters per second. The turn is part of a circle, and they give us a radius in meters. What is the centripetal force? Now, most of the time we've measured force in newtons, and so remember, a newton is a kilogram meter per second squared. So for this to work out in newtons, we have to have mass in kilograms, we have to have distances in meters, and time in seconds. And we do have meters and seconds where appropriate, but what we don't have is mass in kilograms. So let me start off by really jumping back to chapter 1. And so maybe this is maybe the hardest part to recognize of this problem, and convert it into kilograms. So this would be 1.65 kilograms. So that's where we need to start this problem, being careful with our units here. Now, the centripetal force we learned was this little formula. So then it's just a matter of plugging it in. 1.65 kilograms, speed of 9.55 meters per second and squared, and a radius of 14.5 meters. And if you look at your units, you'll have the kilogram, you'll have meters squared here over seconds squared, and then down here you'll have another meter, which will cancel off 1 in the top, and you'll be left with kilogram meters per second squared, which is the newton. So like I said, the important step here was to convert grams into kilograms for this to work out right. The meters already worked out right. We've got meters in the top and meters in the bottom, and they cancel off to just, we'll have 1 meter, which is perfect for the newton. And then the second squared is also perfect for the newton. So it's only the kilogram we got to be a little careful with, but it does come out to be newtons. And so now I can put in my numbers, 1.65 for the number, 9.55 squared for the number, and the 14.5 for the radius, and we're looking at about 10.4 newtons for the answer. So again, kind of a straight plug and chug, other than just be careful with that unit. So reasonable problem. And again, I guess I'd still say 28's the hardest one so far. Then we got into the chapter on gravity and the tides. Here it says the gravitational force between, or what is the gravitational force between these two planets, Saturn and Jupiter, when they're this far apart. And again, G m1, m2 over r squared is what we called Newton's universal law of gravitation. And so we'll need to know the masses, we'll need to know the distance between them, and we'll need to know this gravitational constant G. And I'll start there. The gravitational constant G is the 6.67 times 10 to the negative 11. Its units are Newton meters squared over kilograms squared. And let me pause right there, because that's essentially telling me then, since it's got meters squared in the top, you better put distance in meters and you better put mass in kilograms. Both of them. All right, so let's check that out. The masses are in kilograms, both of them, so that's good. But the distance is in kilometers. So before I start putting anything into my little formula here, let me realize that a kilometer, that K means 1,000. So this is really 10 to the 8th times 10 to the 3 meters, which is 10 to the 11 meters. So the K, kilo, means 1,000. So put it in. Okay, so I'm going to put in the K for kilo. That's going to give me my 10 to the 11th. All right, so putting in my two masses, let's see, here's Saturn, 5.68 times 10 to the 26th. Here is Jupiter, 1.90 times 10 to the 27th. Here is the distance between them, 6.52 times 10 to the 11th. Let me watch my units. Each of these have kilograms, so that'd be kilograms squared. This is in meters, and we're squaring it, so it's meters squared, which, as I said, is why we wanted that, because that meters squared would cancel with that meters squared, that kilogram squared would cancel with that kilogram squared, and we would be left with just the force in newtons, as we would want. So, grabbing a calculator here, I will put in my 6.67 times 10 to the negative 11 for my number. Universal gravitational constant, I'll put in the 5.68 times 10 to the 26 for the mass of Saturn. 1.90 times 10 to the 27th for the mass of Jupiter, divided by 6.52 times 10 to the 11th squared for the distance between them. Hit enter, and we are looking at 1.69 times 10 to the 20th newtons. And like I said, it's kind of like the one above, where it's just kind of a pretty much plug and chug into the formulas we've already learned. But we got to be careful with the units. And so if we don't convert our kilometers to meters, we'll get our exponent wrong by, well, a 3 squared. So you might accidentally get a 26 here for your exponent. Just like over here, you might get your exponent too high. You might get 10,400 newtons if you don't convert your grams into kilograms. You'll be off by 3 exponents, or a factor of 1,000. All right, well, finally, if you guys are still with me, kind of a long review. Maybe you hopefully didn't try to watch it all in one shot, and so maybe you took a little break here. A little over an hour here, but let's finish this up. Now we get into the last chapter here, chapter 6 on momentum. We have this asteroid traveling with this speed. It's traveling towards a bigger asteroid. The bigger asteroid is traveling towards a smaller one with this speed. The two asteroids hit and stick together. And I hope that part just resonates right with you. They hit and stick together. This means that you're saying the momentum before equals the momentum after. And so anytime you see a collision involving things, think, hey, conservation of momentum. So the question is, what is the speed and direction of the two combined asteroids? So we're going to get this clump here, depending on what they're made out of. A lot of them are very brittle and they kind of explode at these speeds and pieces, fragments go over. But if they're a little softer material and not, well, a lot of them are metals too, so they're malleable. So they may hit and deform without shattering into pieces. That would be nice, but a lot of times this speed, even the metals become shattered. But well, actually, these are small seeds compared to, well, maybe not. Anyways, let's just put it together as the problem describes here. But we've got our first mass, 70.7 kilograms. Traveling with a speed of 725 meters per second. So that's the momentum of the first one. The second one has a mass of 89.8. And I didn't give myself enough room. Bummer. Let me just drop the kilograms. See if I can squeeze in the speed here. And the speed, and here's where a little bit of thinking, other than just blindly plug and chug, comes into play. Is remember it's times velocity. Momentum is mass times velocity. It's not speed, it's velocity. So it has positives and negatives. And so this is a smaller one. It's traveling towards it. So if I put a plus here, then I got to put a minus there. Or the other way around. If I put a minus here, I got to put a plus here. They definitely go in opposite directions. There's no requirement of which one's positive and which one's negative. That's just a human choice. But they got to be opposite, so one has to be positive and one has to be negative. So I'm going to call the original one positive, so the other one, the bigger one, is negative. Now, of course, if they stick together, we can think of it as one big object where the mass is the 70.7 kilograms plus the 89.8 kilograms. And then multiply whatever speed they would have, would give me my momentum. So the momentum of the two combined together right here must be the same as before they collided. So if I grab my calculator and go 70.7 times 725 and add to it the 89.8 times, and there it is, negative 325. I get a total momentum of 22,000, and I'll just round it up to 73 kilogram meters per second for the units. So then if I divide it by this total, which would be 70.7 plus 89.8, I will get a final speed of 137.7 meters per second, because kilograms would cancel off on each side. And notice it comes out to be positive. So that's the magnitude of it, and it says speed and direction. And so maybe I'll just put here the direction is going to be the same as the smaller one was moving. Because the smaller one is what I called positive. Now, had I called it negative, I would have got a negative, and so I still would have came up with the same conclusion, that it's moving in the direction that the smaller asteroid. So the smaller asteroid, even though it's smaller, it actually has more momentum. And so by the time they collide, the smaller one, I guess, wins the battle, if you will, and it goes in the direction, because it's carrying with it more momentum. Not because it has more mass, in fact, it has less mass, but because the speed is so much more than the other one, resulting in more momentum, and then the whole thing goes off in a direction of the smaller one. Well, finally to the last one, same idea. It is a conservation of momentum. We have an interaction. This time they don't stick together, so perhaps it's a little bit harder. It also has that additional fact that, hey, remember, momentum is mass times velocity, not speed. So there's positive and negative numbers we have to worry about. Because the first part of this says that we have a 1/4 of a kilogram rubber ball is thrown at a stationary cart. So the stationary cart would have no momentum because its mass times velocity would be 0. And the rubber ball would have 1/4 of a kilogram times its speed. And if we keep reading, the rubber ball hits the cart at a speed of 14 meters per second. So that would be the momentum before the collision. Then they have a collision, and in this case, it comes in and bounces off. So the rubber ball is by itself traveling, and this is an important piece also. Let's see, bounces off the cart, traveling back to the thrower at a speed of 8. So notice it says the speed is 8. I need to put in the sign of a -8 for the velocity. So it travels in the negative direction. Now, the cart would have a mass of 1.5 kilograms and then times some unknown speed. And so if we take the 1/4 times 14, that's the total momentum. And this momentum's actually negative. So when we bring it to the other side, it becomes a positive number. And so this is a 1/4 times 8. So the momentum of this cart by itself is more than the 3.5 of the total, because again, that's going to be a negative, and that's got to be a number then greater, because the two of these together have to be the 3.5. So this one by itself has to be 5.5. So then if I divide it by 1.5, I get a speed of 3.67 meters per second. And doesn't really say the direction. It just says what is the speed. So I guess technically I'm done, but I will point out that this came out to be a plus sign. So its direction would be my direction that I've defined as positive, which is the originally thrown direction of the rubber ball. So the cart goes in the direction originally thrown. So if it's thrown from left to right, the cart would take off left to right. And then, of course, the ball bounces back the other way. That's why we put the negative there. All right. Hope you did well on the test. Hope you learned a little bit by going through the video solution.